All right, we'll record it. All right, this is section 10.5 and Alex. Question 10. This is the question, correct?
Yes.
All right. In one lottery game, contestants pick 6 numbers from 1 to 29, 1 through 29, and have to match all 6 for the big prize in any order. You'll get twice your money back if you match 4 out of 6 numbers. Let's see. If you buy 2 tickets, what's probably matching 4 out of 6 numbers? Let's see. It's all 6 for the big prize in any order. You'll get twice your money back if you match 4 out of 6 numbers. All right. You match 4 out of 6 numbers. If you buy 2 tickets, what's probably matching 4 out of 6 numbers? Okay. All right. So when you play this lottery here, you have 1 through 29, 29 numbers to pick from. And you're interested in matching what was it? 4 of the 6 numbers, I believe. Okay. So 4 of the 6 numbers in any order. Now this is any order here. All right. So we're trying to match 4 out of the 6 numbers for this game. Now, how many ways can you, how many tickets can you buy for to play this lottery game if there's 29 numbers and you have 6 numbers on a ticket? Okay. Well, there's 29 in combination with 6 numbers, because you see order does not matter here with this particular game here. So the probability of matching 4 numbers out of, I believe there's what, 5 numbers, or excuse me, 6 numbers here. Let's take a look here. The probability of matching 4 numbers is equal to, now each ticket must have 6 numbers on it, and you want to match 4 numbers in any particular order. So it's going to be 6 in combination with 4 ways of matching the 4 numbers. Six in combination with 4 ways of matching the 4 numbers. And there's 2 numbers that, 2 other numbers that are going to be on your ticket. Okay. And so this is going to be times let's see here. So there's 29 numbers total, but you're matching 4. So that leaves you with 29 minus 4, or 25 numbers left in combination with 2 ways to pick the last 2 numbers. So wait a minute here. That's 29 minus 6. Hold on a second. Yeah, this should be, that's not right here. This is not right. This is not right. It's 29 numbers we have to choose from, but 6, 4 numbers, 26. Hold on, something's wrong here. 20 numbers. Matching 4 of the numbers. 4, 4. This should be 4 in combination with 4 here. All right. So a number of ways of matching 4 of the numbers. 4 of the 6 numbers in any order would be 4 in combination with 4. But again, order doesn't matter. That's why we're using combinations here as opposed to permutations. So this could be 4 in combination with 4. But we had 29 numbers to choose from. We chose 4 of them. So 29 minus 4 is going to be 25 numbers left. And of the 25, we have 2 other numbers we have to choose from because it's a 6-number ticket here. 4 plus 2 is 6 numbers. And this is going to be divided by how many ways can you choose a 6-number ticket from 29 numbers? Order doesn't matter. Well, that's going to be 29 combination with 6. Okay, so let's get on our calculator and figure this out here. Dial this up. And again, you might want to put parentheses around this whole thing here to be safe. Doesn't hurt. So 4 in combination with 4 times 25 in combination with 2. 300 divided by 29 in combination with 6 numbers. So your probability is kind of small. It's 0.00063. And actually, this goes on a little bit further, 1552. So that appears to be the probability of matching 4 numbers here. And you can see that that is a very, very small probability that that is going to happen. Yeah. Let's see. 6 and 4. Let me double check I made this right here. 4 and 5 numbers. 4 of the 6 numbers. It's 4 of the 6 numbers. Any 4. And it did say match 4 numbers, right? Let me double check this. 4 out of 6 numbers match 4 out of 6 numbers. Okay, hold on. This is still not right. We're matching 4 out of the 6 numbers here. This would still be, this would be 6 in combination with 4. This is no, still not right. This is 6. This guy is going to be 29 minus 6, which is going to be 23 numbers left over to choose from. And this is 23. So this is going to be 6. And this is going to be 23. Six, 23, these add up to 6 here. Okay. And again, make sure you put parentheses around that. So it's going to be 6 in combination with 4 times 23 in combination with 2. And that's going to be divided by 29 in combination with 6. All right, your odds are probably a little bit better. 0.007989137. Now, if you buy 2 tickets, this is if you buy 1 ticket, but if you buy 2 tickets, then all you're going to do is you're going to multiply this probability by 2. So we're going to double this probability. 29137. 2. And so this is going to give you 0.015978275. And I don't know what they want you to round it off, but that should be the probability matching 4 out of 6 numbers. Where order doesn't matter if you buy 2 tickets. Okay. And so again, this is 6 in combination with 4. All right. Where these 4 numbers can occur in any order amongst the 6 numbers that are chosen. And this is the number of ways that the 2 remaining numbers can be arranged or chosen from 23 remaining numbers. Okay. All right. If you have any other questions, liaison, from these problems, I'll be more than happy to answer them.
I wanted it in fraction form is the whole thing.
They wanted that in fraction form?
Yes.
Okay. Are you going to be able to stay on the line for a couple minutes after class?
Yes.
We'll get this in fractional form. Okay. All right.
Okay.
So let's get going on 11.1 here, which is entitled Gathering and Organizing Data. All right. Now, this is going to be, again, breaking ground with basic statistics. Chapter 11 is actually a little easier than most of the chapters we've covered in this whole course. So hopefully this will give you an opportunity to, leave this class with a decent score, at least on the last exam. All right, statistics. Basically, statistics involves collecting data and analyzing data and drawing some sort of conclusion from the data. Statistics is a science. It's a branch of mathematics, a relatively young branch of mathematics. Some of the oldest branches of mathematics are the geometries and the trigonometries that date back to thousands of years ago. But statistics is a relatively young branch here. And the statistical method basically involves collecting data, organizing the data, whether you use a graph or a picture or maybe a table, summarizing, rather analyzing the data by subjecting it to various statistical analyses, which fall under the realm of statistics known as inferential statistics, and then drawing some sort of a conclusion about what your data is trying to tell us about the parent population from whence it was chosen. All right, now the first thing we need to understand is the difference between a population and a sample. When you get into statistics, all the time you are referring to a sample versus a population. A population consists of all elements that are under study, whereas a sample is a smaller subset of all these elements. Let me give you an example. Suppose that my population was consists of all the degrees that are being pursued at Mott Community College. that would be considered my population. Suppose that I reach in, I pull out a good simple random sample from this population, and my sample represents only those who are going to get a degree in culinary arts. That would be considered a sample, right?
Are we supposed to be seeing a PowerPoint right now?
Yeah.
If not, that's okay. We just can't see it.
No, you are supposed to be seeing it. Okay. All right, I apologize for that. Section 11.1, gathering and organizing data. This PowerPoint is on Canvas for your viewing here. Again, we collect data and we then subject it to the statistical method, which involves organizing the data, analyzing the data, drawing some sort of conclusion from our analysis, and then presenting our findings. Okay. Population is a set that consists of all subjects under study, whatever that might be, and a sample is a smaller subset of the population. All right, there's statistics is basically broken up into two main topics. The first topic is descriptive statistics, which involves rather us computing various statistics from populations or samples, such as measures of central tendency, the mean, median, and mode, or measures of dispersion and standard deviation, the mean absolute deviation, the variance, okay? Those are all descriptive statistics. And the definition of a statistic is any quantity that is computed from a sample. That's the definition of a statistic. Whereas the definition of a parameter is any quantity computed from a population. So a statistic, again, by definition, is any quantity that is computed from a sample. So if we collect a sample from a parent population and compute its mean or average, that would be a statistic. If we collect all data from a population and compute the average or the mean of the population, that would be called a parameter. Right? The field of statistics, or the topic of stats, is broken down into two main categories: descriptive statistics and then inferential statistics. Inferential statistics involves reaching into a parent population and pulling out a good simple random sample, and then analyzing that sample, and then taking the results from that analysis of that sample and using it to infer something about a population parameter value. Often inferential to do this, often inferential statistics will have us building maybe a confidence interval or conducting hypothesis testing. Now, we're not going to go that deep, ladies and gentlemen, into statistics because we simply don't have the time, and this course is not a stats course. But if you're interested in delving a little bit deeper into statistics, Math 150 here at Mott is our formal elementary statistics and probability course. In that course, you will dive quite a bit deeper into inferential statistics in constructing interval estimates or confidence intervals and conducting hypothesis testing for various population parameters such as the mean or the standard deviation or the population proportion. Okay. So descriptive statistics and then inferential statistics are the two main categories or topics in statistics. There is also an offshoot from statistics that enables you to work with ordered paired data. When working with ordered paired data, you basically are doing correlation analysis and also regression analysis. And correlation analysis involves collecting an ordered paired data set out in the real world, and then basically computing some statistics called correlation coefficients that enable you to determine how strongly correlated the X and Y data is, or how strongly associated the X and Y data is to each other. Regression analysis involves trying to build an algebraic equation that models your ordered paired data set And this is called, normally you just study linear regression in elementary statistics, trying to fit a line to ordered paired data. And the equation of that line is usually written in slope-intercept form. We call that the least squares regression line. If your data, ordered paired data you collect in the real world, if it's scatter plot, after plotting the ordered paired data points in the XY plane, if your scatter plot suggests a parabolic signature, like a U-shaped graph, then you'd probably want to use a quadratic regression and try to fit a quadratic function to your ordered paired data. Some data exhibits a cyclical nature. For instance, average high temperatures throughout the year in this neck of the woods. The temperatures basically emulate a sine or cosine wave from trigonometry, in which case you'd want to use trigonometric regression on the data to try to model that data. Okay. But the nice thing is, once you model the data according to some sort of an equation, you can then use that equation for predictive purposes. All right. Now, the first thing we're going to show ourselves is how to organize data according to what is called a frequency distribution table. So we'll go out in the real world, we'll collect our raw data, and oftentimes when we collect our raw data, it comes at us all mixed up, unordered, unsorted. But a frequency distribution table is a very powerful way of organizing your data and helping you see some interesting facts from the data very quickly, as opposed to sifting through raw, unsorted data. We're also going to show ourselves how to build a stem and leaf plot, which is yet another very useful method for organizing data and having it be more discernible as to what it's trying to tell us. All right, now the first frequency distribution that we're going to investigate is a categorical frequency distribution. Categorical means non-numeric, okay? Most frequency distributions are numeric, but sometimes they're non-numeric, they're categorical. Categorical involves like names of things or colors of things like that, non-numeric labelings. Right. Here is a data set that represents 25 volunteers who basically indicated their blood type. And there are, let's see, there's type A blood, type B, type AB, type O blood. What makes this even more complicated is the fact that all of us also have some sort of a RH factor attached to our blood type, rather whether it's RH positive or RH negative. But they're not including that in this data set. They're just including the blood types here. Okay. From this data set, we are going to build a categorical frequency distribution table. And the first column of our table is going to be the listing of the blood types, A, B, O, and AB. The second column is going to be a tally column where we keep track of the number of blood types that fall in each category here. And then we'll have a frequency column at the end, which sums up our tally marks. So how many blood types are type A? Well, from this data set, we can see that there's 1, 2, 3, 4, 5 that are type A. Now, with these tally marks, the fifth tally mark should always be a diagonal. So you should always have no more than groups of 5 tally marks. So notice that there's 5 type A blood, and type B blood, there would be 7. Again, these tally marks, for every 5th tally mark you count, the 5th tally mark becomes the diagonal of the first group of tally marks, right? The reason why we do this is because then it's easy to count your tally marks. You count by 5s then. All right, so notice these tally marks for all the different blood types are indicated here. And then the last column would have us converting those tally marks to numbers, and that's your frequency column. Okay, so this is called a categorical frequency distribution table. Now, the nice thing about this table is with one glance, we can determine very quickly what the most common blood type is. And what is it? It's type
Oh,
O, and the least frequently occurring blood type appears to be what?
AB.
AB, okay? Now, this table here, ladies and gentlemen, enables us to determine that information very quickly. And it's therefore a lot more powerful to use tables to organize your data, because sifting through raw data that's all unsorted could be very tedious to ascertain any sort of useful information. Oftentimes when we collect data sets out in the real world, we're not just collecting 25 observations. Oftentimes we're collecting hundreds or thousands or even millions of observations or data points in our data sets. With such massive data sets, ladies and gentlemen, it becomes even more important that you organize the data in some fashion. Otherwise, you're not going to be able to tap into the important information that is basically being hidden within the data. Okay? And the larger your data sets, obviously, the more important it is to be able to turn it over to a computer system that can work with numbers very quickly as far as sorting or ordering your data. All right. But normally our data sets in this course for this chapter are pretty small, where, I mean, we could analyze the data or deal with it in a manual sense. But our calculator, our TI-30XS, can still do some statistical routines and can help us out for some computations. Now, if you are going to take Math 150, elementary stats and probability at Mott here in the future, you may want to invest in a TI-84 graphing calculator, because that calculator has been blessed with a tremendous number of powerful statistical functions and routines. Okay, unlike the TI-30XS, which is a much more basic calculator, which does not have all those powerful routines and functions. I think they require the TI-84 anyways when you take the Math 150 course here at Mott. All right, now a grouped frequency distribution table deals with, rather as opposed to categorical frequency distribution table, deals with numeric data. And most of our data we do collect in the real world, in all honesty, is usually numeric. Okay, but not always. You know, like with the blood types there, that was categorical. This was a non-numeric data set here. But normally our data is numeric in nature. All right, now with a grouped frequency distribution table, because we're collecting numerical data, ladies and gentlemen, the type column, if you will, becomes a little bit more complicated. It's not just a listing of like names or, in this type, blood types. Our first column of our frequency distribution table usually consists of classes, and each class has a lower numeric endpoint and an upper numeric endpoint. And so it becomes a little bit more complicated. For instance, suppose we were gathering weights of all the people in our class here. We would have to come up with numeric classes so as to categorize all the weights that we collect from our classroom. Maybe we would have one class that starts at 100 and runs to 119 pounds. Then another class goes from 120 to 139 pounds, et cetera, et cetera. These are called class intervals. And each interval has a lower endpoint and an upper endpoint. Now, when you build a grouped frequency distribution with classes and numeric data, these are some very important things that you need to make sure that you adhere to. If you don't adhere to these points, then your frequency distribution is no good. It's essentially worthless. All right, number one, ladies and gentlemen, when you build a group frequency distribution with numeric data, number one, you got to make sure that your classes, you have no more than about 5 to 7 classes. This PowerPoint says up to 15 classes. I've never seen a group frequency distribution with 15 classes. You want to keep it to about 5 to 7 classes. All right. Number two, you want to make sure that there's no overlap between your classes, which is critical. The reason why that is I'll show you why, because if you had a weight class that runs from like 100 to 119 pounds, and then your second class runs from like 116 to like 100 and like 27 pounds or something. The problem is if you have somebody that has a weight of, let's say, 117 pounds, what class are you going to put them in? Technically, they would belong in what? Both classes here. But that's a major problem. Major problem is the fact that you'd be double counting data, and you cannot do that. There's 2 cardinal sins in the field of statistics. Number one, you never want to fabricate data. Number two, you don't ever want to eliminate data or brush it under the rug, so to speak. Those are 2 no-nos. Just remember, ladies and gentlemen, when you work with numbers and data and statistics, numbers don't lie. People lie, but numbers don't lie, okay? And so it's very important when you do statistical analysis that you have integrity about yourself in your investigation when handling the numbers, okay? Now, there have been many people down through the annals of time that have fudged the data and basically fabricated data to paint a picture that they wanted to paint. Some people are actually spending time behind bars as I speak because of fudging the data and or maybe sifting off numbers or dollar figures into their own secret little bank account. That's called fraud, by the way, okay? So, ladies and gentlemen, when you work with numbers and data, just remember, don't fabricate data, don't double, triple count data points, and you don't want to throw data points away. The only time, okay, it might be meritorious to throw data points away is if they are adverse outliers in your data set. And you'll learn in Math 150 how to determine mathematically whether a data point qualifies as being an outlier. All right, but that's the only time. So just remember those things there. So the problem we have here with overlapping classes is that we would be double counting a data point, or maybe even triple counting if we had adverse overlapping of classes. And that's no good. So you got to make sure your classes never overlap. Number two, you want to make sure that no data point is forgotten, that every data point has a class to fall in. And the fourth thing is you want to make sure that your classes all have the same width. That's very, very important. If you have one class that runs from 100 to 119, and then you have another class that runs from 120 to, let's say, 400, well, ladies and gentlemen, which class is going to gobble up all the data points? Well, the class that's going to gobble up all the data points is going to be the widest class. And what is the widest class here?
$120 to $400.
That's right. That's the widest class. And that is going to, therefore, consume most of your data points. And so you're going to have a grave distorted view as to the distribution of your data points within the data set. So the key is make sure that all your classes have the same width. They're all of equal width. Okay. The last thing here is indicating that if you round a couple of data points off to the tenths place, maybe 1 decimal place, then you should round all your data points off to 1 decimal place. You want to be consistent in how you round your data. Okay, don't round a couple of data points to the tenths place and then decide to round a couple of other ones, maybe to the millionths place. Don't do that. So these are very important things to remember when building a group frequency distribution for numeric data. Okay. All right, to illustrate the construction of this very valuable table, we have the record high temperatures for each of the 50 states in degrees Fahrenheit. So each one of these temperatures represents a record high temperature for a particular state that has ever been recorded by the National Weather Service. And these temperatures are in degrees Fahrenheit. Now, I don't know which temperature pertains to which state. That's not important. Bottom line is we have 50 record high temperatures, one for each state of the United States here, okay? What we're going to do is we're going to build a grouped frequency distribution data table for this data. That's what we're going to do. Now, in doing that, the starting point here is you might want to determine the range of your data. So what's the maximum data point in your data set? The maximum.
I would say 134.
134. All right, what's the minimum data point in your data set?
100.
Okay. All right. Good. And so, ladies and gentlemen, we're going to, first of all, determine the range of our data set, which is the difference between the maximum and the minimum data points in your data set, which is 34 in this case. And it's important to know the range because that's going to steer us in the correct direction as to where we start our first class off at, and how many classes maybe, we want to use to build our frequency distribution table here. Now, if we use a range of 5 degrees and we have if we use a width of 5 degrees for each class and our range of our data set is 34, then we're going to have to use at least 7 classes. Do you agree? Because 5 times 7 is 35, which will cover the required range of our data. All right. If we choose a width of 4 degrees for each class, then we're going to need at least 9 classes to encompass the range of our data here, right? Again, you don't want too many classes in your distribution table because if you have too many classes, then your distribution table is going to be no better than if we were to just sift through the raw data to try to ascertain important information. And you don't want too few data classes because if you have too few of them, then it's also going to be worthless in giving us an idea as to the distribution of your data points throughout the data set. So you want to strike a happy medium. 9 classes is maybe a little high. I'd go maybe with 7 classes, 5-degree width for each of the classes here. So notice our minimum data point is 100 degrees Fahrenheit. And so where would I start my first class off at? Could I start my first class off at 100 degrees? The answer is yes. That'd be a great place to start. Could you start your first class off at 99 degrees? The answer is yes. There's nothing wrong with that because your 100-degree measurement would fall in that first class. But ladies and gentlemen, could you start your first class off at 102 degrees? What would be wrong with that?
Higher than the lowest one.
That's right. You start your first class off at 102 degrees, you're going to be losing some data points from your data set. And like I indicated, it's one of the 2 cardinal sins. You don't want to lose data. So no, can't do that. So how about we start our first class at 100? And each class has to have a width of what, 5 degrees? So therefore, if the lower limit of our first class is 100, then the lower limit of the second class should be 105. Because 105 minus 100 gives us a width of each class of being 5. The lower limit of the third class should be 110, lower limit of the fourth class, 115, et cetera, here. Okay. All right, so here we have it. We're going to use how many classes here? 1, 2, 3, 4, 5, 6, 7 classes, and each one is 5 units wide. Now, how do you determine the width of a class for a frequency distribution table? Well, there's one of two ways. One way is to look at the difference between successive lower limits of each class. 105 minus 100 gives us a width of 5. Or you could look at the difference between successive upper limits of each class. 109 minus 104 also gives us a width of 5. All right, so that's how you can determine the width of classes of a frequency distribution table. You don't want to take the upper limit minus the lower limit. That's no good. No, it's the difference between successive lower limits or the difference between the successive upper limits will indicate the width of each class. So these classes are all 5 units wide. And let me ask you this next question. Is there any overlap between any of our classes? Any overlap?
No.
So we're good in that department too. There's no overlap. Now, another thing is you'd have to come up with some sort of a rule if you have a data point that lies between like 104 and 105 degrees Fahrenheit. Now, the rule you come up versus the rule maybe somebody else comes up might be different rules. That's not important. What is important is the rule you come up with, you had better apply it equally and fairly to every data point in your data set. For instance, if your rule was a measurement of 104.5 or less than this, and you're gonna, with a data point like that, you would throw it into this class here, then you better apply that rule to all your classes, into all your data points. All right. So in other words, if I have a temperature of 104.5 and put it into this first class, but if I have a temperature of like 109.5 and then throw it into this class, no good. You're contradicting your rules here, okay? Your rules are not consistently applied. So if your rule says 104.5 degree temperature should be included in this first class, and if you have a temperature of 109.5 degrees, you better include it also in this class, not this one here. All right, that's the key. Be consistent with any rule you come up with for any data points that have values between any endpoints of your classes. All right, so now that we have established our classes that we're going to use for this frequency distribution table, now it's just a matter of going back into the raw data set and basically tallying up where our data points fall in each of these classes. All right, for instance, how many temperatures have a degree measure of 100 to 104? 100 to 104. Let's see if we can find them. 100 to 104. 100 to 104. 100 to 104. 100 to 104. Do you agree there'd be how many? There'd be 3 of them. Do you agree 3 observations that fall in that first class? 100 to 104, unless I missed any. I think I got them all, correct? 3? So
That's all I see.
what's that? Yeah, that's what you're going to do here. So as I would notice, there were 3 observations among the 50 that do fall into first class, and therefore its frequency count is 3. And notice they tallied up all the other temperature measurements in that data set and indicated in what class they fall. And then they converted the tally marks to numeric values. Again, notice your tally marking should always have the 5th tally mark as being a diagonal to wrap up a group of 5. That makes it easy to count your tally marks if you do it that way. Okay? So, very quickly, what was the most common high record temperature for states? Between what and what?
110 and 114.
There you go. See how quickly you can ascertain that information as opposed to sifting through this raw, mixed up data, ladies and gentlemen. And this is still a small data set. Like I said, normally your data sets have thousands or millions of data points in it when you collect it. And so there is no way you're going to take your eyeballs and scan through your data, if there's hundreds of thousands of data points, which are all mixed up, and be able to ascertain any sort of useful information from it. You have got to try to organize your data some way so that you can start to extract the important information that's, you know, being hidden in your data points. And if a categorical or a frequency distribution table is a great way to begin to do that. All right, what was the least common record high temperature for the continuous?
130 to 134.
130 to 134. That's right. Okay, so this is called a frequency distribution table that involves numeric data. Another very useful plot is called a stem and leaf plot. When you build a stem and leaf plot, you have to dichotomize your data set. That's such a big word. What does it mean to dichotomize something? To dichotomize something means to basically split it up into two halves, okay? You're going to have a stem portion of your data, and then you're going to have to allocate what you're going to call your leaf portion of your numeric data. Now, what we call the stem and leaf portion of our data really, in large part, depends upon what kind of data we're collecting and how it looks. All right. For instance, if you collect 2-digit numbers in your data set, an ideal thing to call your stem would be maybe the tens digit. And maybe the ones digit would then be allocated or called the leaf portion. If you collect data that, ladies and gentlemen, is rounded off to the tens place, then you might want to call the stem portion the ones digit, and then the leaf portion could be called your tenths digit after the decimal point. Okay, so it really depends what type of data you collect as to what you're going to call the stem versus the leaf portion.
So it can switch.
Yeah. For instance, here's another authentic data set that represents percentage of adults that had been fully vaccinated against COVID-19 as of July 1st, 2021. They want us to build a stem and leaf plot illustrating the data or organizing the data. So I have a question for you. Based on the data points that we collected, what would be an ideal thing to call the stem portion versus the leaf portion? What do you think? Well, the way the data presents itself, ladies and gentlemen, all the data points have a ones digit and a tens digit. So I would probably be tempted to call my stem portion the tens digit and my leaf portion the ones digit. All right, so that's what we're going to do. So notice we have our stem portion of our data, and our stem portion consists of data that ranges from what? The 30s, the 40s, the 50s, and the what? The 60s. Do you agree? 30s, 40s, 50s, and 60s? So we'll call that the stem portion of our data. And then the leaf portion is going to be the ones digit. All right, the ones digit. Okay. Now, just like there were some very important things to adhere to when building a frequency distribution table, there's also some very important things you need to adhere to when building a stem and leaf plot. Number one, you want to make sure that your stem values always increase from top down, strictly increase. Got to be in order, increasing strictly from top down. You want to make sure that your leaf values always strictly increase from left to right, always. Those are two major requirements for any stem and leaf plot. Notice my stem values strictly increase from top down, and my leaf values also need to strictly increase from left to right. Okay, so let's begin here. The 30s. Okay, so what would be the, you know what, I'm wondering if I could maybe snip this data set. Hold on a second here. That way I don't have to keep flipping back to this slide here. Just bear with me for a second here. Okay. Now let's see if I can bring that data table up here. All right, here we are, ladies and gentlemen. So, what's the minimum data point that's in the 30s? The minimum.
30?
Do you see a 30 in here? Yeah,
Yes.
right there. Okay. So we start our leaf off at 0. There's a data point that is 30. Cross it out. Any other 30s? If not, what would be the next larger leaf for our 30s?
I see a 33.
33. Cross it out. Keep track. Any
34.
other 33? Any other 33s?
All I saw was that one.
Okay. Is there a 34?
Yes.
34. Is there another 34?
I don't see one.
Is there a 35? I see a 35 here. Any other? I see a
Yes.
35 here. Do you agree? Any others? All right, so here's what I want you to do, ladies and gentlemen. I want you to complete the stem and leaf plot for this data here. This will be classwork number 1. Go ahead and complete this. All right, classwork number 1.
1, 2, 3, 4. 53. Six. One, 2, 3. 56. 57. 58. No. But they're all 56s. 2. I see 2. 55. Didn't get it all. I didn't get the whole data set.
What's wrong? What's wrong?
I didn't get the whole data set.
Can you see it now?
Yes.
Sorry about that. All right. Well, hold on a second. Hold on. Hold on. All right. Can you see it now?
Yes.
All right.
I don't know how, but I'm missing 8 of them.
8 of them? You're kidding me?
Yes, I'm missing 8 of them.
I'll tell you what, let's go look at the solution here. Now, I want to point something very important out here. Why is this stem and leaf plot worthless? Right here.
Because the digits are out of order.
Which ones are out of order? The stem portions or the leaf portions?
The leaves.
The leaves are not ordered from left to right. This is worthless. All right, don't do that. Okay, let's go on down here. Now, your stem and leaf plot should look like this when all is said and done. Notice the stems increase strictly from top down, the leaves increase strictly from left to right. That's the way your stem and leaf plot should look. The nice thing about a stem and leaf plot, ladies and gentlemen, is that you can determine precisely every data point in your data set. You just have to have some patience. In other words, 30 is a data point, 33, 34, 35, 35, 35, 36, 37, 37, 37, 38, 39, 39, 39. You have a data point that's 40, 41, 42, 42, 42. You have how many data points that are 52? How many observations were 52?
4.
4. Everybody see how this is working here? Okay. This is called a stem and leaf plot. All right. And down here at the bottom, they give you a key that is to be used to know how to read your stem and leaf plot. They have a 4 and they have a vertical bar and then they got a 3. And then they tell you that this is to be read as the data point 43. Everybody see that there? Okay. So how many, what was the largest observation in this data set? The largest?
66.
And what was the minimum?
30.
30. Okay. All right. How many 55s were in the data set?
3.
3 of them. All right. So this is called a stem and leaf plot, ladies and gentlemen. So first you have to determine what you're going to call your stem portion and what you're going to call your leaf portion. And then you have to make sure your stems increase strictly top down and your leaf values increase strictly from the left and right. That's called a stem and leaf plot there. All right. You got to be careful because it does take time, as we're finding out, to build a stem and leaf plot. So it requires your diligence and your perseverance, all right, to build one of these stem and leaf plots. So the larger your data set is, the even more patience is needed, okay? So does that make sense there, that stem and leaf plot there? Stem and leaf plot. Okay. All right. So let's go to our book and see if we can have some fun here in our textbook. So. Okay. All right, ladies and gentlemen, here's the first one I want you to do, and this will be classwork number 2. At a college financial aid office, students who applied for a scholarship were classified according to their class rank. FY represents first year, SO sophomore, JR junior, SE senior. Construct a frequency distribution for this categorical data. This is non-numeric data. I want you to build a categorical distribution table for this data set. Your first column should be the class listing of the student, whether they are first year, sophomore, junior, or senior. The next column should be a tally count, and the third and last column should be a frequency numeric count for each category. You go ahead and do this. We'll call this classwork number 2. Go ahead. Number 23, classwork 2.
think I got it.
All right, Liz, I want to show you an interesting website that I found here, and I will attach this link to Canvas. It will enable you to reduce fractions. Now, our TI-30XS can only reduce fractions as long as, you know, the numerator and denominators are not that big. When you start getting into problems with combinations, okay, some of your numerators and denominators are going to be humongous, in which case your TI-30XS will just turn it into a decimal and say, I forget, you know, and basically just call it quits and will not reduce it as a fraction. So you're left kind of holding the bag, trying to, you know, figure out how am I going to reduce these horrendously large numbers. I found this neat little website, and this is how you can reduce fractions. And this bar here is where it says reduce fraction. You just left single click your mouse, and then you can type in a fraction. For instance, I'll type in like 99 over 33. Now, how did I do that? How did I type in 99 over 33? On my keyboard, I typed 99. Then I hit my division key. And what is the division key? It's this key right here, okay? So I typed in 99, I hit this right here, this slash key, and then type in 33. That'll report it as a fraction 99 over 33. Let's go ahead and do that. So 99, get my division key, and then 33. And then you just click on go, and it will reduce that fraction down. It reduced it down to 3. Okay, suppose we, and now to do another problem, all you have to do is go back up here in this bar and click on it, and then hit your backspace key to erase that fraction and type in another fraction. Suppose we had this nasty fraction, 7590 division bar over 475,020. Now, reducing this fraction is no fun, and your TI-30XS is going to fail in doing so. But if you just type it in and hit go, this thing will reduce even massive size fractions. Reduced it down to 253 over 15,834. So I'll provide a link on Canvas, and on the dashboard, I'll provide a main link to access this website so that you can reduce fractions regardless of the size of the numerator and denominator, okay? All right, so keep this in mind if you're doing anything on Alex and your combinations are giving you big numbers in the numerator and denominator, and your TI-30XS, it fails to reduce it down to a fraction, but just turns it into a decimal. That happens, okay? So you might have to revert and use this here. Or you can reduce it manually. You realize that both numbers end in a zero, so 10 would divide into both the numerator and denominator. And then you could get it down to 759 over 47,502. Then you could realize, hopefully, that 3 divides into numerator and denominator, takes it down to 253 over 15,834. So it could be reduced manually, but I'm just saying if you want to use this, go ahead and use that. It'll speed things up. All right, let's take a look at the problem here that I wanted you to do. There you go, ladies and gentlemen. That would be the categorical frequency distribution table for this school student body here. And we can see that 18 first-year students qualify for this scholarship, whereas only 4, what's SC again? SC was that SC or SC? SE. That should be SE, right? Only 4 seniors qualify for the scholarship. That should be SE. All right, anybody get this correct here?
I did.
Yes.
All right, great. All right, so onward we go. Now, ladies and gentlemen, this data is numeric here. Number 27, the ages of the signers of the Declaration of Independence are shown here. Age is approximate since only the birth year appeared in the source, and one has been omitted since his birth year is unknown. Wow. Construct a frequency distribution for the data using 7 classes. Now, so that we're all on the same table, ladies and gentlemen, I want all of us to begin the first class at 27. I want all of us to begin the first class at 27. And then I want the width of our classes to be 7. So the beginning of the second class will be 34. Then the beginning of the third class will be what? What's 34 plus 7? That'll be what? 41. All right. I want you to build a frequency distribution table with 7 classes. And I want you to start the first class off at 27. So you're going to go from 27 up to what? 33. Et cetera, et cetera, et cetera. You fill in the other remaining 7 classes. And then I want you to build a frequency distribution table, have a tally column and then a frequency column. We'll call this class work number, I guess it's 3. Okay. Go ahead and do that problem right there. 27.
Really 27.
Mm, 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 mm. 6. Six, 7, 8, 9. 1, 2. So 43. 4, 6, 7, 8, 9. I'm a little mixed up on this. Seven. 27. There's none there, none there, none there, none there. One so far. Seven, 3.
Well, does anybody got it out there? Are we done on this or are we still going?
Six. One. 3. 5, 6. Where's 7? Six. 7. One. No. I'm a little confused on it.
We'll check it out in a second.
Two, three, 6. Six. 6. 7.
Let's take a look here. So when all is said and done, ladies and gentlemen, this should be it here. There you go. That would be your frequency distribution table for that numeric data there. 7 classes. The width of each class is 7 units wide. It's 34 minus 27 or 40 minus 33, 7 units wide. Okay. Right there. Sorry about that. Okay, yeah. So the width is 34 minus 27 or 41 minus 34 or 48 minus 41 or 55 minus 48 or 62 minus 55 or 69 minus 62 or 40 minus 33, 47 minus 40, 54 minus 47, et cetera, et cetera. The width is 7 units for each class. And there you go. You just want to make sure that all these data points do add up to the total number of observations in your data set. If they don't, that means that you either fabricated data or you lost data points, and that's a no-no. So you just want to make sure that this sums up to the number of observations in your data set. Okay. All right. So you can see that these problems do take a little bit of time to construct. There's no doubt about that. Let's see here. Let's go down and see if we can do a stem and leaf plot down here somewhere. Okay. All right, ladies and gentlemen, I'd like you to do a stem and leaf plot for number 35. The National Insurance Crime Bureau reported that these data represent the number of registered vehicles per car stolen for 35 selected cities in the United States. For example, in Miami, one automobile was stolen for every 38 registered vehicles in the city. Construct a stem and leaf plot for the data and analyze the distribution. All right, I want you to build a stem and leaf plot. The stem portion will be your tens digit, and the leaf portion will be your ones digit. Go ahead and build a stem and leaf plot. This will be our last classwork right here, number 35.
6. Six. Seventies. Three, four, five. That's 76. Three 69s. That's easy that I'm looking for. Two 89. Two. 3, 4, 6, 8, 9, 10, 13, 14, 15, 16, 17, 18, 20, 21, 22. Two, 3, 4, 6, 7, 8, 9, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 25, 26, 27, 28. I'm still missing 7. Oh, there's 69s. And another 89. 2 89s. I'm mixing myself up. 50. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. Missing 6. See, a couple more 83s. How many 80s are there? There's some 70s. I put those on there. 66 is out there. 83. Oh, missing me. Missing yours. Oh. See an 89. 35. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 1, 2, 3, 3, 4, 5, 6, 7, 8, 9, 10. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. Missing 4.
All right, let's take a look at what the answer would be here. So there would be your stem and leaf plot there for your data. All right. So what we covered today is we began to look at ways of organizing data, both qualitative and quantitative data, into what are called distribution tables, and also building a stem and leaf plot. Now, next week, we will begin to become a little bit more computational in the field of statistics after we look at some more very interesting graphs that can be used to further organize data. All right, so I'll stay on the line, liaison, for a couple minutes. If there's any questions, let me know. And Alicia, if you want to stay on the line and go over that problem, we can go over that problem in section 10.5, okay?
Okay.
All right. All right, you guys have a great weekend now.
Okay, so I was doing 10.8 homework,
Yep.
question 5, and I got it wrong. So like you know how you can like try another one, it gives you another problem, and then you can just do it again. For this problem, it won't let me have another problem. Like, and I don't want to submit my assignment when I could have gotten it right, but it just won't. It won't let me try another problem.
All right, which assignment 10.8?
10.8 question 5.
Okay, 10.8 question 5.
Yeah, for Reagan
And
Cordes.
all right, and your last name is Cordes?
Yes.
10.8, number 5. All right, I'll look into that. And if it doesn't allow you to do another problem, I'll just give you credit for that problem, okay?
Okay, thank you, because I know it's all due tomorrow.
I'll check it out, okay? All right.
Thank you.
All right, Alicia, do you want to look at that problem or?
Yes. Hang on a second. I'm submitting my homework, my classwork.
I just had a question about the classwork from one before this one. Could I see that one? Because I didn't get to check and see. I stepped away.
That one was, hold on a second here. That was this one right here, number 27,
Yeah, I did it right. I was just trying to make sure.
frequency distribution table, okay?
Mhm.
All right. All right, let me know when you're ready, Alicia.
Ready. I'm just
Okay.
confused on how to do number 10 on 10.5.
All right, 10.5, number 10.
Yes.
One more quick question. You did open up all those assignments and quizzes at one time, right?
For which ones now?
The ones that are all posted yesterday. Because I
Yeah,
didn't see it. I was making sure I didn't miss something. I'm like, where all these come from?
yeah, all these have been opened up, all right?
Okay.
And the quizzes have been opened up too and everything, all right? So,
All
there.
right. I
All
was
right.
checking to make sure I wasn't behind.
All right, 10.5, number 10. Notice it gives us a different problem here, correct?
Yes.
I mean, with just different numbers, but it's the same type of problem. So one lottery game, contestants pick 5 numbers from 1 through 22 and have to match all 5 for the big prize in any order. You'll get twice your money back if you match 3 out of 5 numbers. If you buy 7 tickets, what is the probability of matching 3 out of 5 numbers? Okay. We got to find what the probability is for buying one ticket, all right? So you have 22 numbers to choose from, 3 out of 5. You got to match 3 out of 5 in any order. So the probability matching 3 of 5 is going to be 5 in combination with 3 times, now there were 22 numbers to select from. So once we select our 3 numbers, there's only going to be, once we select our 5 numbers, there's going to be only 17 numbers left. with which to choose the two other remaining numbers. This is a ticket that has 5 numbers. We're trying to match 3. This is divided by 22 in combination with 5. Okay? Five number ticket there. Is making sense?
Yes, so far it
All
is.
right. Now, in order to compute this, you're not going to be able to do it all at once if they want a fraction. You got to piecemeal this. So you got to do 5 in combination with 3. And that's going to give you 10. Times 17 in combination with 2. That gives you 136. Downstairs, 22 in combination with 5. 22 in combination with 5. It gives you 26,334. And then we have the unenviable task of trying to reduce this here. Now, this gives you 1360. The TI-30XS is not going to reduce that. So what I recommend you do now is take this fraction. Now, wait a minute. We're buying 7 tickets too. So the probability with winning that set with 7 tickets is going to be 7 times this. 1360. Um, okay. So it's going to be 7 times 1360, which is 9520. And that's going to be divided by this here. This should be your probability of winning with 7 tickets. Now, we're going to take that to this website that I put a link on Canvas to. We're going to take that fraction to the website and we're going to have it reduce it, okay?
Okay.
So let's go to that website. And like I said, I put a link on the main dashboard here. It says fraction reducing site. Okay, just click on this. Click on this. Click on this up here, fraction reducing site, and away we go. All right, so now let's come up here. Select that and just hit your backspace key to delete it. Now we'll type in our fraction. And our fraction was 9520, division key, 2/26334. And then just go over here and click on go, and it should reduce that fraction. And it's been reduced. It's been reduced down to 680 over 1881. Now we'll go back and enter this number in, okay? And see if we got it, okay? See how we did that?
Yeah. Yes, I did.
Now, so we're going to go back here, and we're going to type in our reduced fraction, 680 over 1881. Check the answer, and what do we got? We got it correct. You see that?
Yes.
There you go. That's how you do the problem.
I was getting confused because my calculator is not made to reduce.
Yeah, unfortunately, it's not reducing these big numbers. You know, they should just allow it to be entered in as a decimal, in all honesty. I don't understand that at all.
So now I can go back to that problem and then go into the fraction reducing.
Yes, use that fraction reducing site. That'll help.
Because that's what was confusing me. I didn't know how to translate the I didn't know how to convert the decimal into the fraction.
Mhm. So that should work, okay?
Okay.
All
That's
right, any other questions?
if I get into any other homework assignments to where I need questions, I will email you.
All right.
All
I'll
right.
let you go then.
All right. Thank you.
All right, bye.
Have a great day.
You, bye.
Bye bye.